So we know that this simple random walk starting from A with absorbing barriers 0 and A plus B, this Markov chain, gets absorbed either at 0 or at A plus B with probability 1. Okay. So this is, okay, we know, meaning I've given it as an exercise for you. I've given also a hint, so you should be able to do it, I think. Now, as I said, since tau is finite with probability 1, where tau is the time for the Markov chain to get absorbed for the first time, so that's basically the infimum of m bigger than or equal to 1, such that xm is either 0 or xm is A plus B. Since tau is finite with probability 1, x tau essentially gives the final value of the Markov chain. In other words, it gives you the value at which the Markov chain will finally get absorbed in. Okay, so it has to be either 0 or A plus B. So therefore, with probability 1, x tau is either 0 or A plus B. That just follows from the fact that tau is finite with probability 1. Now, of course, the question is, what is the chance that x tau is equal to 0? And this, if you go back to the gambler's ruin problem, this is just the question that we asked in the gambler's ruin problem. Namely, what is the chance that A is ruined? That's same as asking, what is the chance that this Markov chain gets absorbed at the value 0, which is probability of x tau equal to 0. Now, of course, if you know this probability, given that tau is finite with probability 1 and therefore x tau is either 0 or A plus B, it will be immediate that probability of B is ruined is also be obtained for free, because that is 1 minus probability of A is ruined. Okay. So this says that, you know, this particular fact that I gave you as an exercise in the gambler's ruin context means that the game will stop with probability 1. Either A will be ruined and then B will win, or B will be ruined and hence A will win. Either of these two events is going to happen with probability 1. Therefore, the game cannot go on forever. The game has to stop at some point. So therefore, probability of B is ruined is just 1 minus probability of A is ruined. So in any case, we still have to find this probability, and we'll do that using Markov chain theory. So this will take some time. We have to develop some notation, some terminology, and then a lot of theorems, and then only we can solve this problem. But keep this in mind, that these kind of questions we are trying to answer. Okay, so now instead of absorbing barrier, we can have a reflecting barrier. Now, what does that mean? It means it's the same thing if you are in one of the interior values. So by the way, this is a Markov chain on the same state space, all integers from 0 to A plus B, which starts at A. So the initial distribution is delta A. In the transition probability matrix, there is only 2 changes essentially. So if you are at a point in the interior, any of the points in the interior, 1 to A plus B minus 1, no change at all. You just go to one of the nearest neighbors with probability half. There are 2 nearest neighbors, one on the left, one on the right. You go to them with equal probability. The change happens if you reach the boundary values. If you reach 0 or if you reach A plus B, what happens? If you reach 0, you immediately send back to 1 with probability 1. Okay, so that's what this says. On the other hand, if you reach A plus B, you immediately send back to A plus B minus 1 with probability 1. So instead of getting absorbed, you're actually reflecting it. Okay, so let's see the picture. Let's see the transition diagram. So it doesn't matter where you start from. At this point, you can forget about that. If you're in any of the interior values, you're going to either go to left or go to right with probability half and half. If you're in any of these values. But then at the boundary values, you're just reflecting the walk to the nearest interior value in the state space. So if you're at 0, so if by any chance you reach 0, immediately you'll be in the next step, you'll be at 1. Similarly, if you're at 5 at some step, immediately at the next step, you will be at 4. Here, therefore, there is no absorbing state. No state is absorbing the Markov chain. And this Markov chain is going on forever. This is going to go on moving forever. Okay, so suppose you start at 2. So A is 2 and B is 3, say. So this is how the transition diagram looks like. So as I said, the only difference is that earlier, whenever you reach 5 or 0, you get absorbed there, you stay there forever. Okay? Here you don't do that, you just go to the nearest neighbor. That is possible. So with probability 1, the boundary values only have one nearest neighbor, you just go there with probability 1 once you reach one of the boundary values. So this is called simple random walk starting from A with reflecting barriers at 0 and A plus B. It's reflecting because the moment these two barriers are reflecting the walk. Now this you can sort of guess this, and we'll prove this also, is that you start at 2, and since you are reflecting, you're going to go back and forth again and again. Okay? And therefore, you'll actually hit your initial point, namely 2 in this case, infinitely often. On the other hand, in the case when in the simple random walk with absorbing barrier, you'll get absorbed in one of them eventually, either 0 or A plus B, and therefore you will come back to your starting point only finitely often. Okay, both of these statements that I'm making are with probability 1. So with probability 1, this particular Markov chain will come back to 2, or come back to the initial starting point infinitely often. On the other hand, the previous one, the gambler's ruin Markov chain, will come back to the starting point only finitely many times with probability 1. Okay? We'll prove these things. I'm just giving you a prelude of what's going to come. Now, as I said, the coin does not need to be unbiased. It can be a biased coin, and therefore you won't have simple random walk anymore, but you will have what is called the nearest neighbor random walk with either reflecting or absorbing barrier. Okay. Now, in this case, the transition probabilities and hence the transition diagram will change accordingly. So what will happen is all of these blue probabilities will be the same. Okay. On the other hand, all of these green probabilities would be the same. So this would be, these probabilities will be 1 minus these probabilities. Okay. So it depends on the coin, what is the probability of obtaining a head and what is the probability of obtaining a tail. So this will change, the transition diagram will change, or the transition probabilities will change accordingly. But the model will still make sense. And we can ask, in the absorbing barriers case, we can ask the same question. We can ask, what is the chance that A is ruined? And by the way, we'll be able to show, this is something I didn't write here, but we'll be able to show by using the same argument that, in fact, it's easier to show in this case that it gets absorbed with probability 1. So first, an exercise, show that in the biased case also, if the coin is biased also, then also the Markov chain, nearest neighbor random walk with absorbing barriers, okay, that one will get absorbed in one of the barriers with probability 1. Okay. Now the question is, what is the chance that A is ruined? In other words, what is the chance that it gets absorbed at 0? Okay. Now this is again a question that will be answered in this course. Okay, so I've given you just one exercise and no homework assignment so far, because I want you to know a little bit more on Markov chains, and then only I'll give you a homework assignment. But do solve that exercise. It's a nice exercise from probability theory 1. And all you need to do, you need to bound tau by a suitable random variable. And if you can do that, then you can get a very easy proof, even in the case when the coin is not biased. The coin is not unbiased. Okay? Okay, so that's where we are going to stop today. From next time, we have seen enough examples. I think we have seen, I think 11 examples, right? The last one, example 11, yeah. 11 examples of random walk. Some of them were trivial and some of them were non-trivial and so on. And we have seen many questions about Markovnians as well. So what we will do is, next time we'll start the basic properties of Markov chains. Okay? And then once we develop a theory, we'll come back to these examples and we'll see that what our theory gives us in each of these examples.